Yeah. We are defining this definite integral from A to B as a limit of this mesh going to 0. Now, this sigma notation looks a bit complicated to the beginners, but is actually not really complicated, in that sense. What we have here is a product of, we got an infinite series of terms, or n number of terms in this example. I never said n goes to infinity anywhere, doesn't matter. In fact, when you say mesh goes to 0, mesh happens to be the maximum width of a subinterval, correct? So, if that maximum width goes to 0, that means every one of the other widths also goes to 0, which means the number of intervals has to become infinite. So, n actually goes to infinity automatically because of this. We don't have to write that specifically. This implies that n goes to infinity. Then this term is a series, summation of series of n number of terms. Each term is a product of the value of the function at some point, call it tk, and the interval width actually. So that means we are taking every subinterval and a value tk within that interval. Function value if you take, that is the altitude, and multiply, you get the rectangle area. Actually, you are getting a rectangle area here. Each of those terms is the area of one of these rectangles. And the height of the rectangle will be that value of function ftk, which can be the left value, or it can be the right value, or it can be the maximum value within that interval, doesn't matter. Somewhere around there, basically, that's what is that. So now when you write like this, you will find these gaps here between the actual area which I am interested in. Area under the curve is what my interest is. But if you add the areas of all these rectangles, you can see some gaps appear below, some may appear above also, depending on what value that you select for the tag, tag value. Doesn't matter. Eventually, when the subinterval size goes to 0, tends to 0, that gap will automatically go to 0. So eventually it will become the area of the area under the curve. So that is the definite integral is the area under the curve between 2 points. That is the definition. Now, like I said earlier, there are a couple of small subnotes we can make before we go and state the actual theorem of calculus. What is called the fundamental theorem of calculus. I would like to state that. But before we do that, I can make a couple of small observations, and that is because of the area only. Now, I have drawn conveniently, when we draw some diagrams on the board, this is the Euclidean plane. When we draw it, I say we got an x-axis and we say we got an y-axis and so on. It is natural that I have drawn the curve f there, right? So, somewhere there. I could easily have written the curve below the x-axis, right? So, in which case what happens? Value of function is negative, f is negative. So, if the entire curve is below x-axis, you will find actually you are multiplying a negative quantity by xk minus x minus 1 is always positive, correct? Because our limit b is higher than limit a, so is all the, I have written that relationship earlier saying fundamental relation is a equal to x0, which must be less than x1, must be. I added that equal to also, which I removed in the center, but you should retain that equals because in the event when the mesh goes to 0, n goes to infinity, that difference goes to 0, really speaking. So, less than equal to is fine. So this relationship is there. So, it's a positive quantity. Any value of x minus the previous value of x will be positive. F of any value under the x-axis will be negative. So this Sn will be negative number actually. So area can be positive or negative. Above x-axis is positive, below x-axis is negative. And in fact, you can have a combination also. That is, I have got a function which partially above x-axis, partially below x-axis, possible. And when you say I want to find the area between these 2 points, it will be the area above this x-axis minus the area below the x-axis. That will be the actual value that we are going to find. So that is fine, as long as we take care of the sign. Now, that also brings us to a convention that supposing I want to write definite integral from B to A, not A to B, B to A. I want to start from B and go towards A, the same fx dx. What is going to happen? Take this f, or original f, for example. I am starting from B and going this side, which means all these relationships that I have written will be greater than or equal to. Correct now? Which means xk minus 1 will be negative in this case. F is positive, so you get a negative area. So it will be negative. And that negative value is exactly the same as this positive value that you had. So this must be equal to minus integral from A to B of fx dx. So we'll take this as a, geometrically it looks correct and obvious, intuitively correct, but we'll take it as a convention. We'll take it as an axiom if you want. So we'll say this. This is one aspect. Now second aspect is, supposing between A and B I got a third point, you can call it C, for example, which means I can now integrate from A to C fx dx. So I will get one area between A and C. I got from A to C, actually I shouldn't say between, it is from A to C I got one area now, to which I will add another area which is from C to B fx dx. From C to B, so there is another area. If I add these two areas, geometrically it is obvious, I must get the total area. So this must be equal to A to B. You can call this also a convention, or you can say this is correct. You can take it as correct. So that is one other aspect. Now the next aspect is we take the same A to B of fx dx and modify this contents here. Supposing I take absolute value of that fx and integrate. What happens? We get what are called inequalities. Let me show that here. Couple of small examples. There are many such inequalities different mathematicians have proved as correct. But the whole basis is that area business. One example we'll take. Supposing I want to look at from A to B integral mod of fx dx. That means I take the absolute value of f and integrate it over that. That means f can be above, also will be considered positive, below also will be considered positive. If all are above, is fine, it's the same value. But if part of it is below, like I have shown earlier, I got part of the curve below, here it will add this part as a positive area, and this part also is subtracting, it will add actually, because we are taking the absolute value of f. Whereas if I take the integral from A to B of ordinary fx dx, now this maximum will be the total area, but it could be less also, correct? No? So because of that subtraction, so I can say this will be greater than or equal to. This is one inequality. So A to B absolute value of fx dx must be greater than or equal to A to B integral fx dx. Because some terms are negative, value will always become lesser. All terms are positive, value will be always higher. So the same token, one more inequality I can write, you can even guess. Supposing I say from A to B, I take fx squared. You can call it f squared x, or better to write it as a square of dx. That means I take each value of fx and square it and then integrate it. Now square, you know whether f is positive or negative, square will always be a positive number, correct? No, so you understand? Which means this will be greater than or equal to A to B fx of dx whole square. another inequality. So like that you can write n number of such inequalities if you want. Or I'll just show you one other example of an inequality. Sometimes in some proofs you might need these inequalities as basically lemmas, no? That is small theorems that you want to use. Supposing I got two functions. I got an f, I got a g. Right? If you want to see the plot of those, I can show you. So I got the x-axis, I got an f. This is f. Some graph is there. I got a g, another graph, right? Now, geometrically, you can see the entire g is below f, no, the entire g. That means, actually, in the interval, so how do you define that? This is a domain, common domain under which I want to integrate both. So you got the domain AB, closed interval, for any x inside that closed interval AB, I am saying if f of x is less than or equal to greater than or equal to g of x. You always add that equal to because sometimes it might touch it also. All I am saying is g will never go above x. It can touch it but it will be below most of the time. Supposing this is the condition. Then what can you tell about integral from a to b of fx dx versus integral a to b of gx dx? What can you say about that? Can I say this is greater than or equal to? That is, area under the f is greater than or equal to area under g. I mean, it's obvious from this diagram, but then remember, I could easily have them below also. Negative values also is possible, and that sign should automatically take care of it. You can verify that. I have an f here and a g here. Area under the f is a negative quantity of this much. Area under g is a bigger negative quantity. Therefore, that greater than or equal to still holds good, correct. So this would be another inequality. So like that, there are so many inequalities which you can define when you have this definite integral. So now I think it is time to state the fundamental theorem of calculus, which comes in two parts. Okay, two parts. So what? So we look at the first part. We start with the same diagram. We don't go outside this so-called area diagram. No? So everything is based on this area diagram. So I got this x-axis. I got some kind of a function, whatever that is, f. Now in this interval, I am starting from 0. At the beginning point, and some point here, doesn't matter, whatever point is that, I can mark that as x only. That means I am trying to find an integral, definite integral from 0 to x. Left hand side is 0. 0. From 0 to x, I want to find integral 0 to x of fx dx. This will be a function of x, of course. If x increases, this will also increase. X decreases, this will also decrease. Of course, if it is above, if it is below the x-axis, the negative value will increase or decrease or whatever. So, the same thing holds good. When that is the case, then we don't even write this 0 and x. That means the short form, that is the notation, integral from 0 to x of fx dx. I mean, here I have shown x itself is varying from 0 to x. If that is confusing, you can change the name here. You can call it, I have got a variable called y, integral fy dy. That means I got a point y on the x-axis. This can change from 0 all the way till x. The same. It's just a symbol there. I can write fx dx also, or I can write fy dy 0 to x. If that is not confusing, I will write back the old fx dx only. this is normally written. Convention is we don't even specify 0 to x. We just say integral of fx dx, which is actually means 0 to x of fx dx. This is known as the indefinite integral. Because this is a function of x itself, right? Because when x increases, I get a different area, right? So this is the area function. Actually, this is a area function. Area under the curve. We can give a name to it. I will call it, let's call it capital Fx. That means capital Fx is the area of the segment below the curve of f between 0 and x. That's the definition of fx. So now I got two functions. One is fx, old fx that we had. Now I've got a capital Fx also. So what is the relation between these two functions? Is established by theorem of calculus. So first, to start with, what we will do is, I got fx, right? The area in the original function f. Supposing I do a small displacement for x. So I'll get a rectangle there, right? Thin slice. Correct? That means I change the x. Because of that, I have added an area there, right? Now, what is the area of that slice? What is this area? Very simple. Is the area under the curve till x plus the delta x. So there is the small distance is delta x. Okay. So area under the curve till x plus delta x minus area under the curve till x. Correct? Now, if I subtract the small area from the big area, I will get the area of the slice. So therefore, this will be f of x plus delta x minus f of x. Correct? Area under the curve till x plus delta x is f of x plus delta x. Area under the curve till x is f of x. And the difference gives me the thin slice, right? So now I divide this by delta x and take limit. So we take limit of this. Limit of as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. Tell me what I will get. This is the definition of a derivative. Correct? Is fx. Sorry, is f prime x. Capital F prime x. Correct? And the first part of the theorem of calculus says this is equal to fx. That is the derivative of the indefinite integral is the original function itself. So that's why fx is also known as antiderivative of fx. Okay, if that equation is confusing, what we will do is I will write a slightly different diagram. That means we go and plot the function capital Fx itself. I had plotted f here. Supposing I go and plot the function capital F, that is the area function. So at x I got a value which is the area till x of this original curve. The height actually. This height is actually this area. Similarly at x plus delta x, so this is delta x. I got another height here which is the area of the curve till x plus delta x. Correct? So which means this height, the difference in height, this is this first height is fx, second height is f of x plus delta x. Correct? And what we have plotted is f. And what is f prime? Is the instantaneous rate of change. Is f limit of delta x goes to 0 of f of x plus delta x, same minus f of x divided by delta x. Correct? The same, we'll get the same limit. Derivative of the area is the height of the curve. Now, if you define, for example, fx as antiderivative, what is the second part of this theorem? Is supposing fx is a function which is continuous and differentiable in an interval, and fx is the antiderivative. Then integral a to b of fx dx will be fb minus fa. The same, if you look at the original function of f and you got the 2 points, let me take these as 2 different points as the domain a and b, and integral from a to b is the area under the curve, right? Now, fb, value of the antiderivative at the point b is the area from 0 to b minus area from 0 to a. The difference should give you fx integral fx dx. That is the second part. So both are approximately same. I don't know how you can find out the difference, but in any case, now this is the primary purpose of the whole business of differentiation. Is I want to find out the area under the curve. All I need to do is find the antiderivative of fx and just subtract the 2 values of that antiderivative from the end point to end point. I'll give a very simple example. Supposing I want to say what is integral from 0 to pi by 2 of sin x dx. That means we got a sine curve. What is sine curve? Is 0 at 0 and pi by 2 it is 1. Correct? So I am talking of the area of the curve under the sine, or you can go till pi also if you want, which will give you including the other part. So this is pi. Sin pi is 0, sin 0 is 0, sin pi by 2 is 1. So I want to find out the area under this curve, under the sine curve between 0 to pi. How do you find out? Integral 0 to pi of sin x dx. I need the antiderivative of sin x now. So what is the antiderivative of sin x? That means which is the function when you derive it, I should get sin x. I should get back sin x after differentiating a function. If you recall our discussion, d by dx of cos x was minus sin x. Therefore, minus cos x is the antiderivative of sin x. So, this is equal to minus cos x is the antiderivative, right? And we have to evaluate from 2. So, we write that. From 0 to pi by 2 is what we have to evaluate. That is, we evaluate at pi by 2 and subtract the value of evaluation at 0. FB minus FA. So, which means equal to minus cos pi by 2 minus, not pi by 2, I said pi, correct? So, minus cos pi minus of minus cos 0, correct? Minus cos pi is the value at FB, minus cos 0 is the value at FA. So, I just subtract FB minus FA. So, what is cos minus pi? Minus cos pi. Cos pi is minus 1. So, this is plus 1 plus 1 equal to 2. Where is the confusion here? I got a to b fx dx, which is 0 to pi sin x dx. I need to find the antiderivative of sin x. There is no direct method for finding antiderivatives. We have a direct method for finding derivatives. So, just think back on all the derivatives that you find and see, did you find a function for which the derivative was sin x? No, that is what you have to see. And we do find that it's a cos x, but actually you didn't get sin x. We got a minus sin x, so I have to write a minus cos x. So if you differentiate minus cos x, you will get sin x as a derivative. Therefore, minus cos x is the antiderivative of sin x. So this is the capital Fx actually. I want to evaluate this capital Fx at b, that is pi, minus evaluate capital Fx at a, which is 0. Therefore, it is minus cos pi minus of minus cos 0. And cos pi is minus 1, cos 0 is 1. Substitute 1 plus 1 will be 2. 2 will be the area of the circle. That curved area above the sine curve will be 2. And half of that, up to pi by 2, if you do, it will be 1 actually. No problem there. So, this was the primary reason for doing derivative. Actually, our interest is antiderivative. So, that means you have to keep deriving lots of functions and keep a record of all the derivatives of the functions on one side. Left side is functions, right side is derivatives. Now, actually, that is not the mapping we want. So, tomorrow now you are trying to solve some problem where you need to do some integration. I'll give you a couple of small examples which our old Greek mathematicians did by some crazy method of limits and so on, which you can do it like this, like a snap, so quick using integration. So, for doing integration, now you say I got a function, you look for the function not on the left hand side of your table, but on the right hand side of your table. And if you find an entry there which is your function, obviously the antiderivative will be on the left. Corresponding left side will be the antiderivative, and just take the value of the antiderivative between the two limits and subtract, you will get the integral, right? Now, we will take a simple geometric example just to prove my point, the usefulness of integration. Now, integrals, like I said, actually our interest in any problem is definite integral. We are always interested in finding out a to b integrated from a to b of fxx. This is what we really want in any problem. But then, for doing that, we need a general purpose function, capital F, which is the antiderivative, is the indefinite integral actually. So, we look at indefinite integrals as a way of listing functions on the right hand side of fx. So, we always put fx on the left side of the column, and so fx is one side, corresponding indefinite integral on the right side. Sorry, I wrote the other way around. Left side you write the indefinite integral, right side you write the function, whichever way you want, doesn't matter. So, when you find a function and find the integral, for example, I found sin x as a function, right? Right on the left side now, correct? Differentiate it, and what do you get? we get cos x. Correct? F prime is F, so it's correct. So now tomorrow, you say I got a sin x differentiated to cos x. Integral of cos x is sin x is cos x. So, if this is fx and that is capital Fx, or this is a capital Fx, this is fx, which is correct. So now if fx is sin x, no, this should have been minus. I think I made a mistake. If this is sin x, this will be cos x. Okay. Now example, we'll take a sphere. Volume of sphere, simple. As a very simple example, geometric example. So I got a sphere, I am interested in finding the volume. How do you find the volume of a sphere? You cut that into thin slices, very thin slices and integrate. So we got a slide, or you can take hemisphere, because now it is both increasing and decreasing. So probably you can work with one direction. So we'll take a hemisphere, half of the sphere, we cut it into half and cut that into so many slices. Right. One of the sample slices I will write here. This is the center, so one slice. I'll write it big, but actually it is not big, it is just a small, thin slice, correct? You can see that is a disc actually. Each slice is a disc. It's not a perfect cylinder, the edge is slightly inclined, but then when we increase the number of slices to infinity, it becomes thinner and thinner and thinner. We can assume the edge goes to a perfect cylinder. So how do you find? That means each is a disc, correct? So I'm talking one particular disc here, right? So the question is, what is the thickness of this disc? We can take it as delta x or whatever, no problem, or delta y, anything. Here, actually you are interested in the radius. What is the radius of this disc? So that means we draw a line, we draw a right angle triangle. Supposing the original radius of the sphere was capital R, which is same as this diagonal, and I got an angle here. This angle you can call it x. That angle is x. Okay. So that means what I have is something like this. I'll show separately. I got the R, which is the radius of the sphere, and at an angle theta, you can take it as the upper angle or you can take it as the lower angle also, doesn't matter. We can take it as the lower angle only. So, originally this is the hemisphere point and I have gone up by an angle theta, correct? Alternate angle, this will also be same theta. So, what will be the radius, lowercase r, of that disc? You can see r divided by capital R will be adjacent side by hypotenuse. That will be cos theta. Or by capital R is cos theta. Therefore, lowercase r is r cos theta. And what is the volume of this? What is the volume of this disc? Is we are increasing theta by a small quantity, so it becomes thicker. No? So you understand? So volume will be, what is the thickness? Let us assume some thickness for it. I can take it as d theta? No. Pi r squared is the area, correct? Multiplied by the thickness, right? And what is that thickness? We have to calculate in terms of theta, really speaking. So when theta increases by a delta theta, that means I have increased this slightly higher, correct? And what is that height that I get? What is that height? That is same as this angle. Correct? D theta. Pi r square d theta is the volume of this disk. So what we need to do is where r is capital R cos theta. So I think we have to do pi capital R squared cos theta, cos squared theta actually, d theta, integrate it from theta starting from 0. I can go till here or I can go till here. If I go till only pi by 2, I'll get 1/4 the volume. So you can say 4 times 0 to pi by 2 of pi r squared cos squared theta d theta. I think will give you the volume of.
But this R will change for each slice. No?
Huh?
R will change for
Yeah,
each slice.
that is cos theta is changing, no?
Okay.
Our cos theta is changing.
Okay.
Correct. So integrate it, you will get that. Somehow you have to find the appropriate entries in your table and then put that. Okay. So any such areas and volumes and so on, it is easy to calculate using integration. And integration you can only do as antiderivative. That means the derivative table must be there. So we start with the derivative table and then do the use the antiderivative, and the values of that between the limits will give you the integration.
And did you take pi by 2?
Pi by 0 is pi by 2. 1/4 the sphere.
And 4 times, okay.
Assuming 1/4. That's why I multiplied by 4. This will give you the volume. Now, if this looks confusing, you go for a simpler, okay, you take a simpler picture of a cone. Cone is actually simpler. Okay. Cone also you can slice it. Cone has got a radius at the bottom, which is capital R, and has got a total height. Correct? You can write inverted cone if you want. That might probably simplify the equation. So the top radius is capital R, and the height is h. A cone. This defines the cone, and we want to find the volume of the cone. Correct? Maybe we do that. As usual, you slice the cone into pieces, and each becomes a disk, right? So, supposing I make a disk here. And this distance, at a distance of x from here. At a distance of x, you find it. Now, this angle is known. This angle is tan of that angle is capital R by h. Is the half angle of the cone. Capital R by h. This angle is known. So at a height h, what is it? What is the radius? Radius at a height h. You want to find out. At a height capital H, it is capital R. So this radius, that is lowercase r, is the radius of this small disk, will be capital R by h multiplied by x. Ratio of x by h. X by h is same as r by r. There are similar triangles here. I got two similar triangles here. One is R and X is one triangle, and capital R and height is the other right angle triangle. So both are similar because the angle is theta. No? Angle is common. So I don't even need this tan theta expression, but anyway. So capital R by H into X will be the radius of this, and delta X will be the height. That's the correct direction also for this. That's the dx. So that means the volume will be, we take pi r squared, that is pi multiplied by rx by h whole squared, and dx is that thickness of the disk, and x is varying from 0 to h. Perfect now, correct? This is clear now. Sphere was a bit confusing, and don't feel very sad about that confusion. I'll tell you, because it was confusing to me also. So it's fine. Yeah. Just go back and think about it. You will get that answer correct for sphere. Cone, at least I think, will probably work out all right. So let us see if this is confusing or not confusing. Either way, we should not feel bad. Okay. What we are trying to achieve within half an hour, probably we should not have tried it in the first place. We have tried it. Let us hope it works. Okay, doesn't matter. Either way, it doesn't matter. So now I want to integrate this. Now I have to integrate. In this, capital R is a constant, doesn't change with x, right? H also is a constant. Pi is definitely a constant. You can pull out all those constants outside. So that means equal to pi r squared by h. We take it out. Pi r squared by h squared. Correct? Integral from 0 to h of x squared dx. Now, do you find this x squared somewhere as a derivative? So, when you took a function x cubed and derived it, find the differential, it's like x power n actually. When you did x power n, what did you get? Nx power n minus 1. So now you got an antiderivative there. So for 3x squared, antiderivative is x cubed. Obviously, for x squared, it will be x cubed by 3. Correct. So equal to pi r squared by h squared multiplied by x cubed by 3 is the antiderivative. And this we have to evaluate between 0 and h. That means you have to take the value of this expression at h minus value of the expression at 0, correct? At 0 it is 0. When x is 0, whole thing is 0 anyway, so we need to evaluate at h. And what is that value? Is pi r squared by h squared multiplied by h cubed divided by 3, correct? That is 1 by 3 pi r squared h. This is the volume of the cone. You ask any old Greek mathematician like Pythagoras or Euclid, he will simply rattle it off like we say, what is 7 5s are 35. So what is the volume of the cube? 1/3 pi r squared h. You know. For volume of sphere, you should get 4 by 3 pi r cubed. Anyway, we know the value, but you can always figure out that actual integration process, something like this. You know. So maybe I should not have used theta as the variable there. That's correct, that integral is correct. Only problem was we didn't find it in our table. That was the problem of the antiderivative. So what you do is, this x and dx gave us a nice answer here. So there do the same thing. That is the x-axis, vertical is the x-axis. And I got a distance x, find the radius and dx and then take that. Correct? Maybe we can do that as an exercise. Why don't we do that? It just takes 2 minutes for this. So slightly different approach for this sphere. So we had this sphere and we take a hemisphere. In this, our x is that vertical. We take that x as a vertical. So at a height x, this is x-axis actually, and a variable x varies from 0 all the way till capital R. So I got a capital R here and this is X. So I got a lowercase r and a capital R. Correct. So for a height X, what is the lowercase r? We have to find out. Correct. So what is r? Is square root of r square minus, sorry, what is x? No, r, correct. R is square root of r square minus x square. Any height x, I will get the radius r, correct? And dx, of course, is a thin slice here, and we take the volume of that disk. That is the disk. So we just need to integrate. So what is the volume of the sphere? V is integral from x varying from 0 till r. But then that gives you only hemisphere, so I have to multiply by 2. 2 multiplied by 0 to capital R, and each volume of the disk is area is pi r squared. Pi r squared is pi r squared minus x squared, because r is square root of r squared minus x squared, multiplied by height, which is dx. Thickness, actually, I should call it thickness. Thickness of the disk is dx. This integral should be volume of the sphere. We'll do that. Equal to, I can take pi out. So 2 pi, in fact, pi r squared minus pi x squared. So 2 pi r squared is 1. Entire thing is constant from 0 to r of dx is one part minus 2 pi integral 0 to r of x square dx. Right? Correct. So equal to, what is this? 0 to r of the integral of 1 dx. 1. What is 1 dx? How do you get a derivative of 1? Differentiate 1, x. So x is the antiderivative. So x value at r is r, x value at 0 is 0. So this will be 2 pi r squared multiplied by r minus x squared, we already know, is x cubed divided by 3. So minus 2 pi multiplied by x cubed by 3, which is between 0 to r, so it will be r cubed minus 0. So that is not there. So equal to 1/3, I think you can take as a common factor, and I'll get I get 3 here. 3 r cube minus r cube. So no, 6. I get 6 here. 6 pi r cubed minus 2 pi r cubed.
4 by 3 pi.
This is 4 by 3. Old Greek result, I think we have got. So, like I said, it's only a question of formulating. We got to answer in 3 lines. If you had asked Euclid or Orthodoxus over those great mathematicians of Greece in the BC, CE, that gap years, they would take the same slice they will take and calculate an octagon there and find the area of the octagon and say, I will have this limit, that limit, and sweat it out for 2 days, come up with the same answer. It would come up with the same answer. But this simple integration will give you the same answer that you found. 2 simple examples of these. I think now next we should look at some really interesting examples, right? I will do that, no problem. What we can do next is look at some other examples of integrals. But then I found that one small topic on limits is very simple. is a rule discovered by a gentleman called Johann Bernoulli. Now, Bernoulli family had three mathematicians in their family, two brothers, Jacob Bernoulli and Johann Bernoulli. Then I think the son of Jacob Bernoulli also. All very jealous of each other and trying to outdo one another in mathematics. It's good. Competitive spirit is always nice. Now, Johann wanted a job in Paris, so he went to Paris. France was the center of mathematics at that time. So remember, this so-called center of learning today, probably some US university is some great place. I want to go and do my MS or whatever, graduation level or whatever. But it's not the same. Earlier days, originally started with Persia, that was Iraq, Iran. That was the central place. Around the same time, I think India also was a central place for world education. Anybody wants to learn something, you go to Persia, Iraq, Baghdad. You have to go to Baghdad. Or as a part of the Persian Empire, part of Egypt also was there. So you have to go to Egypt. You want to go to Egypt, you want to go to Baghdad. Decide. So Greeks, the Thale and Pythagoras, for example, Pythagoras is not very clear whether he went to Egypt, went down to Egypt. See, from Greek of Europe, Africa is below that. Now you can see the map tomorrow if you want. So whether he went to Egypt to learn Mesopotamian geometry, or he went to Baghdad or Iran, not very clear, but he went somewhere. So he learned that and started a brotherhood, what we call Gurukula. No? So, and all those boys there, they were called boys only. There were no girls allowed in Gurukulam. Here also, I think girls are not allowed. I think were not allowed. Today, probably there are some Gurukulas. Gurukula is a residential school, basically. And they were called Pythagoreans. So they did a lot of work. Whatever knowledge they learned, they assimilated and made it proper. And we had our friend Euclid who summarized the entire thing and published this book, Euclid's Elements. In Greek, of course, obviously. So the rest of the Europeans, they say, I want to learn mathematics, I want to learn geometry. You have to learn Greek first and read Euclid's Elements. There is no choice. Or you have to go to Greece, what we know today, or it could be Alexandria, which is in Egypt actually, but anyway, it doesn't matter. Alexandria, there are, I think, 20 or 30 Alexandrias. When Alexander the Great, what we call Alexander the Great, he went and fought so many wars. Any new town, he said, we'll start a town here, very nice. What is the name? Alexandria. Everything was called Alexandria anyway. So they had to go there, you understand. So that center of learning has kept on changing. So Alexandria was the next center of learning. In India, Kerala was the next center of learning. In the 15th century, we had the Kerala School of Mathematics, supported very nicely by our Hampi Empire, Vijayanagara Empire. And all those Hakkaraya, Bukkaraya and Devaraya and Krishnadevaraya, they were patrons of music, mathematics, dance, all those things. Our Purandaradasa and Tyagaraja, all those people came because of those encouragements. These people, scientists, require encouragement. Encouragement means money. They need money so that they can have a happy life without working. So they can concentrate on these other aspects of life. Otherwise, morning till night, fellow has got to work just to put food on the table. So then he is not producing anything. He is not a scientist. So obviously, all these activities require people with leisure. Plenty of leisure, brilliant people with plenty of leisure, where they don't have to worry about earning a livelihood. See, that is, you can call them entitled people. Like Newton was one such person. Newton never had to work in his life to make a living. You understand? Unlike people like Ramanujan or Shakuntala Devi, they are very poor. But most of these scientists that you find, Henry Cavendish or Lavoisier, or all these people, they were all lords of the empire. So which means they had a lot of money and a lot of leisure and nothing to do. Of course, 90% of them enjoyed themselves in life and went away. We don't bother about those. But some of those people who are interested in science and physics and mathematics, they had every time in the world. There was one king whose only interest in life was to look at stars. So he used to spend the whole night, never did any administration of the kingdom. No, he built an observatory next to his palace, and where is the king? He is in the observatory now. British king. We did that. Every night. For the next 30 years, till he died. That's all he did in life. But then now the observations he made are useful. Tycho Brahe made those observations because he was a rich fellow. Right? And we got our Kepler to discover laws of Kepler's laws of planetary motion and so on. So that is a different aspect. Place of learning. No? I don't know why I came to that topic. It doesn't matter. Hardly matters why I came. Anyway, I went and said it. So now, this, like I said, the Johann Bernoulli, there are three Bernoullis, Jacob Bernoulli, there is a Bernoulli's principle, Bernoulli's theorem, Bernoulli's something, Bernoulli's number. You will find a lot of Bernoulli stuff. No? Half of it probably was due to Jacob, the other half was due to Johann. Not Johann, Johann, right? Johann Bernoulli. So he wanted a job in France, Center of Learning, and there was a professor there, brilliant professor. His name is Lopita. That is a German spelling anyway. Lopita was the professor there. How he was brilliant, he never actually, I don't think he discovered anything on his own. He used to identify brilliant people around and say, catch the fellow and say, you come and teach in my college, in my university. So that's how he hired Johann. But before actually you can start your job, you have to sign on a sheet of paper saying, whatever you produce in your period here, I can do what I want with it. And Johann, while he was giving his lectures on mathematics, discovered something very nice, a rule actually. We'll discuss that. And what is it called today? It's called Lopita's rule. It should have been called Bernoulli's rule, but Lopita, I published entire thesis. Most of it was lecture notes of Johann Bernoulli. It's fine. Anyway, so we have paid our respects to Johann Bernoulli. That's all I wanted to do. But we should still talk of it as Lopita's rule, because that's the name which everybody knows. What is it? Lopita's rule was basically when you are trying to find some limits, sometimes people hit a wall, saying, I can't find the limit. The limit you are finding because you want to derive a function or find differentiation, whatever, or some limit or some integration somewhere. These limits are always useful. Like, that I can't reach the place, but I want to find out up to that place how much is the value. So, limit. Especially when these limits had a form, what is the indeterminate form? Indeterminate, there are 4 different indeterminate forms. One is 0 by 0, everybody knows that. You can't divide 0 by 0, value is unknown. Or infinity by infinity you can't do. Or 0 to the power of infinity, that you can't do. You don't know the result. Similarly, infinity to the power of 0 has no meaning, and it can have any value. So these are actually called indeterminate forms of expressions, and you want to find, these have no values by themselves, but as a limit, that means I got a fraction of 2 functions, f and g, both of them have got a limit of 0, and I want to find that ratio. So that means limit, for example, f of x divided by g of x, that is our interest. as x goes to some value, it doesn't matter, whatever, a. As x approaches a, if x also approaches 0, gx also approaches 0. So I can't substitute x equal to a here because then it will become 0 by 0. If a is 0, gi is 0. So I can't substitute the value, but I want to find the limit. It's a question. So when x approaches a, if you look at the graph, you will find out how you can find out what is the L'Hopital's rule, and proof for that also is actually from the graph. So let us draw our graph. So I got the x-axis. I want to plot both the functions, and I got a point A here. So I got a function f which approaches 0, probably even crosses it. If you approach it, it will cross also. Go to the other side. So this is our f. Right? I could have shown it the other way around. Doesn't matter actually, because the algebraic sign will take care whether it is positive, negative, everything will be fine. So anyway, just for simplicity, let me write as a function f which is monotonically increasing. And at a point A, value becomes 0. That's what I'm saying. Limit of fx when x tends to A is 0. That is 1. G also the same. So let me show that here. So this is G. G also, as x increases across A, it hits 0 and goes ahead. Now the question is, what about this ratio f by G? What happens? Something very simple. What we do is we drop a perpendicular. We take a small distance. When I say small distance, the tiny distance, we can make it as small as we want. See, we're always talking of limits. No? So this can reach 0. No? Not reach 0, tend towards 0. So when we make it tend towards 0, we get our answer. So we drop a perpendicular. Correct. So what we have here is a delta x. On the x-axis, corresponding to the delta x, you have one delta f, which is the height up to the curve f, and a delta g, which is the height up to the curve g. So now, if you look at f by g, right? What is this g by f? Or fx, when x is expressed delta x, will be delta f. So that is the height, correct? Right? Value of the function f is delta f actually. Because this is 0 point and I got a delta x, the value itself is delta f from x, correct? Similarly, this value itself is delta g. So I'm dividing delta f by delta g. That is what I'm doing here. As x goes to a, which means both these will go to 0. Delta f also goes to 0. Delta g also goes to 0. And this ratio is what I want to find out. How do you do that? We do one multiplication by, remember I got an x going to a, which means that delta x goes to 0, and there is no delta x in this ratio. So we introduce the delta x by delta x without loss of generality. So that limit will be equal to limit. Now I can write delta x goes to 0 instead of saying x goes to a. Delta f by delta x, delta f by delta x is one figure divided by delta g. This delta x can go underneath the delta g. Very convenient. Correct. So now I got a ratio of 2 fellows, 2 is a fraction. Limit of this fraction is limit of the numerator divided by limit of the denominator. And what is the limit of the numerator? Limit delta f by delta x as delta x goes to 0 is f prime, is the derivative. F prime of x. And limit of delta g by delta x as delta x goes to 0 is g prime of x. So, when you say I've got a limit fx by gx as x goes to a will be the same as f prime x by g prime x. That is L'Hopital's rule. Very, very nice. Now if I can substitute x equal to a and find that f prime a is not 0, at least g prime a is not 0. If it is guaranteed, I can actually substitute the value there. F prime a divided by g prime a will be the limit that I want. Sometimes you find even these two are zeros. No? That means f prime x also goes to 0, g prime x also goes to 0. I can reapply the same rule again. That means I am looking at this ratio when x has not reached x, just below that, just not reach a. All other points other than a, it is still non-zero. I can reapply the L'Hopital's rule and write that as limit f double prime x by g double prime x. So I can differentiate any number of times the numerator and denominator and I get my answer correct. We'll take one very simple algebraic example, then you will see. Supposing I want to look at a limit of x squared minus 1 divided by x minus 1 as x tends to 1. Very simple algebraic problem. Now if I substitute x equal to 1, numerator becomes 0, denominator also becomes 0. So it is our indeterminate form, 0 by 0 form, so I can't substitute it. Now how do you find that? We apply L'Hopital's rule, Bernoulli's rule, and differentiate. The same as limit x tends to 1 of what is the derivative of x squared minus 1 is 2x. Minus 1 it becomes 0. And what is the derivative of x minus 1? Is 1. Now I can substitute 1. There is no division by 0. So that means equal to 2 will be the limit. So that means, what it really means is that if x is very close to 1, x minus 1 will be a small value, like 0.001 or whatever. You will find x squared minus 1 will be twice that value, always. Nearly twice, always. In the limit it will become 2. And you could have also found it algebraically, saying this is the same as x going to 1, it tends to 1 of this. You got a standard old format of a squared minus b squared, right? Squared minus 1 squared. We can write that as x minus 1, a minus b multiplied by a plus b, correct? Divided by x minus 1. As long as x is not equal to 1, I know when you say x tends to 1, we always assume x doesn't actually become 1, no? So it is not equal to 1. X minus 1 is a small quantity, same small quantity is above, we can cancel that, no problem, they are not 0, and that will become limit x tends to 1 of x plus 1. Now I can substitute x equal to 1 because I don't need to worry about limit, I can reach and a value will be 2 as before. So that is one simple theorem. Now we come to the actual important thing that I wanted to discuss. This is the simple left-out topic I thought I would discuss. Now here we want to look at a couple of interesting theorems of modern algebra, geometry, trigonometry. Now everything has got mixed up. Now here we have trigonometric functions, we got algebra, we got geometry to show the proof, and geometry we used to define the integral, to define the derivative, which has got a lot of algebra, correct? And trigonometric functions are part of it. So now you can see the whole thing gets mixed up. And there is an analytical geometry where pure algebra is used to solve geometry problems and so on. That's why I said the whole mathematics area has become so vast with all these sub-areas. But I have tried to focus on only those key points where they are all interconnected. So you'll see most of my discussions, you will find Trigonometry will be there, calculus is there, algebra is there. Geometry is also there as part of the diagram. You can see all are there in that. No, the combined, that is where that's the heart of mathematics. No, that combination is the heart of mathematics. Now, on that aspect, when these people, when I say these people, like Euler and Cauchy, for example, they were so busy discovering, inventing new theories, new theorems, new rules, correct now? The massive amount of new technology they were inventing in mathematics. They didn't have time for rigor, you know. Their proofs were half of them intuitive. You know? It's not a solid proof. We need a rigorous proof for everything. Even here also, many times I would have skipped over some statement which you can't, you know. Like the other example I had given some time back, saying Shastry is standing here. 5 minutes later, you find that Shastry is outside that door. I'm there, you know, you can see that. So the question is, nobody saw me actually go through this door. So now, can you confirm Shastry did go through that door? Yes or no? No, that is the question. Intuitively, all of us feel, I think I must have passed through this door. If you ask me, I say, I was there inside, now I am there outside, so I must, no, that must is again not rigorous. I mean, somebody has to actually record it. If we had a CCTV camera, it would actually recorded Shastry going through that door, right? Supposing it is not Shastry, it is our friend Narad. Narad is standing here, 5 minutes later he is outside now. So, did he pass through that door? No, he disappeared here. I don't know where he went and reappeared there, you see. That's why you can't make those kind of assumptions. Or if you are assuming something, you have to say that assumption. I'll give one simple geometrical example. We say this is a real line, right? And when I say real line, what we really mean is that any point in this line has got a unique mapping to the real set of numbers. So we got a real set of numbers represented by the stylized R. Within this, of course, there is one more set of numbers. If you want, I will show you those three, the subsets of R, just to get your thoughts right. It's not needed. So I got this R. R is a huge set. Infinite number of numbers are there. But then within R, there is another huge set of numbers, also infinite number of numbers inside, which is the Q. Sorry. Yeah, Q. Called rational numbers. Rational numbers is a subset of real numbers. And within rational numbers, there is one more infinite number of numbers, is a capital N, stylized N, natural numbers. Natural numbers is 1, 2, 3, 4, integers. 1, 2, 3, 4, up to infinity. Infinite number of them are there. Then you got the rational numbers, which is the set Q, which contains any P by Q, where P and Q are natural numbers. Any combination thereof. You get a series of rational numbers, but then real numbers contain something more than rational numbers. They also contain irrational numbers, right? In this irrational, again, I think there are two categories, but regular irrational and transcendental. But anyway, let's not worry about that. So now the question is, how do we say what are the numbers here? Is a question. So one way of doing that, what I have done during our discussion here, is to say, when you say real line, every point, any distinct point on the real line will always map on to a distinct point in the set R, which can be inside here also. I have not shown that here. Maybe I should rub it off. This can be an integer, it can be rational, it can be irrational. Doesn't matter. So is a distinct point in the real set R. Right? Same way, every real number in the set R maps to a distinct point on the real line. So this is what I have assumed actually. That is enough. But people don't even make this assumption. So this is where the thing is, supposing there is something called the intermediate value theorem. I am coming to that right now. It's the same, Shastry going outside, no? Value here, old value of Shastry here, new value of Shastry is outside. Was there an intermediate value at the door? Is the question, no? Same. So, if you say you got the x-axis here and we plot f, any function f, we find that for some interval, the f value is less than 0, negative value. And we find some other interval, f value is greater than 0, correct? No? So, now the question is, is there a value of f which is 0 is the question. Does it pass through a real point on the x-axis? That, if you assume that is my real line, no? That's what I have assumed. If you don't assume that, you can't assume. Maybe the real line has got a gap somewhere and it passes through the gap, which means there is no 0 value for f, no? You understand? So if you say f has to have a value 0 in between, then we have assumed that. No? So, correct. No? So you either assume the intermediate value theorem, which means if f is less than 0 and eventually becomes greater than 0, it must pass through 0, is the assumption you make. Or you say every point on the real line will always map onto a distinct point on real set. Obviously, it has to pass through because there are no gaps between points on the real line. Correct? No? So, we are going to make this assumption of the real line mapping to real system, and we come to the next theorem of the modern rigorous arithmetic after this. Okay?